Hello, hello, hello. Here we go again. So we're going to do the four examples of speed and velocity here in this first video, and then there'll be another video following up that are the three examples of acceleration that are on the back of the example sheet. One of my suggestions here while you're doing any kind of problems for class is to have an equation sheet in front of you. So take all the equations that we're using for the class, have that in front of you, on one sheet of paper so that you can access them quickly and easily. All right. The other thing that you want to do is make sure that you have all of your units memorized, because that's going to help you in the process of um, selecting your equation once you have your givens and your unknowns. All right. Now, we never want to forget, we are doing the picture, given, unknown, equation, substitute, solve. That is the guess method. All right. If you skip any of these parts, take a chance that you're not going to do very well in the problem. So let's start here. We have a jogger, and he's running from one place to another. All right. So I'm going to draw my picture. If he starts in one location and ends at another location, that means, here we go. We have our runner running along here, okay? And he's going across and from one place to another place, okay? He takes this run, and we know a couple things about this run. Now, if I'm looking up here, I see two pieces of information, all right? And when I say information, I'm looking at two numbers. I'm seeing 1.5 hours, which is the same thing as 5,400 seconds, and I'm also seeing 2.22 meters per second. Now, if I'm paying a close attention to my units here, I know exactly what these numbers are, all right? I can also find this a little bit in the problem, but 5,400 seconds, seconds measures time, so that's one of my givens, is the amount of time it takes this guy to run that distance, whatever it is, all right? So I'm going to label that as t, all right? That is going to take the place of t in whatever equation I use. Now, I have at least three different equations that have time in it, so I can't pick an equation yet. The next thing I see is average speed is 2.22 meters per second. Well, speed is 2.22 meters per second, all right? But I also know that this is a speed because of the units, which are meters per second. So speed 2.22 meters per second. And we want to know, how far does this jogger run? Well, far, this is a distance, all right? And this is what we don't know. So distance is my unknown. Bingo. Well, if I look at my equation sheet, I see that there is only one that that uses all three of these variables, s, t, and d. And so this is speed is equal to distance divided by time. So all I have to do here to find my distance is substitute the values that I've already determined. All right, so 2.22 meters per second for the speed. All right, distance is my unknown, so I'll leave the d in the equation. All right, that's what I'm going to solve for, and the time is 5,400 seconds. And so if I want to solve for d, then I need to get rid of that 5,400 seconds, and since I'm dividing by it, I'm going to multiply on both sides by 5,400 seconds. All right, and that'll cancel the 5,400s out on the right side. Leaves me with just a d. All right, and on the left side here, I'm going to multiply those two values together, my 5,400 and my 2.22. All right, make sure you're doing this in your calculator too. And the answer should be 11,988. Now, what are the units on this? This is a distance, which is meters. But how do I know that it did that? All right, how do I know that I get meters over here on the left side? Well, one thing that I can do is look at this dimensionally at these units. I'm multiplying seconds by meters per second. Okay, and when I do that, notice the seconds are going to cancel out, leaves me with just the meters that I was looking for right here for my answer. So anytime I'm doing a problem, I should be able to do some dimensional analysis and look at my units, and they should always come out to the things that I expect. So I expected meters, I get meters. I must have done my mathematics correctly. So there's the first example of average speed. 11,988 meters was the distance that this jogger ran in 5,400 seconds with a speed of 2.22 meters per second. In example number 2, this one has a bunch of information that is absolutely not useful to us, all right? As I read through the first part, Andy Green in the car thrust SSC sets a world record of 341.1 meters per second in 1997. The car was powered by 2 jet engines, and it was the first to officially exceed the speed of sound. To get the record, the driver makes 2 runs through the course, 1 in each direction. All right? All of that is entirely useless for us solving this problem. One of the red herrings here is this 341.1 meters per second. It seems like that's a velocity we should use in our problem, but it's not. In all reality, the problem starts all the way down here, and it has 2 parts to it. So there's the first run, where the car covers a distance of 1.609 kilometers in 4.740 seconds. And then there's the second part, which is a completely different run, okay? And since these are 2 completely different runs, I'm separating them into 2 separate problems, all right? Run 1 and run 2. And we want to find the average velocity for each run. So that's the other giveaway, that we are doing 2 separate problems here. All right, so as far as givens go, I have a distance for each one of these things, but I'm also seeing that there's some direction. So from left to right in the first run, and from right to left in the second run. And so since I'm seeing direction, I know that I'm also dealing with velocity here, because velocity uses direction while speed does not, okay? So when I start listing my givens and my unknowns, and I'm drawing my pictures, I'm going to make sure that I account for all of these things in my pictures and in my givens and my unknowns. So let's start filling in all the blanks here. Okay, so I have 2 parts. I have run 1 and I have run 2. Okay, and each one of these is a different situation, so they have different pictures. So in the first situation, I have my car, and it's driving from left to right. So I have a car, rocket car, right? From left to right, that's the direction of my velocity. Now the thing that I know about this is I know the distance that it travels, all right? But this is going to be displacement because I have a direction that goes along with it. Now my displacement is 1.609 kilometers, which is 1,609 meters. So I have to watch my units again, all right? And since we're going from left to right, that's the positive direction. That's the right direction, okay? So we have 1,609 meters for our displacement here. How this is different in run 2 is that the car is going in the opposite direction, all right? And it's going in that direction, okay? And so in this case, my displacement, delta x, is going to be a negative 1,609 meters. And so by switching directions, I have to switch that positive and negative. Now the other things that I know about each one of these situations are the time in which they do it. So the time for the first trip is going to be 4.740 seconds. And the time for the second trip is going to be 4.695 seconds. How did I know that those were times? They were in seconds, all right? So I use the units to determine what my variable is. Now that I have this all set up, the big question is, what are my velocities? All right? And so I can split these guys up, and I can solve them separately and find each velocity for this problem, all right? So I use the only equation that I have for velocity. V is equal to delta x over delta t. Now how did I pick this? I have v, delta x, and delta t, all right? All of my givens and my unknowns in one equation. All right, so I substitute the values that I have in here, positive 1,609 meters, all right, and 4.740 seconds. Over here, same equation, delta x over delta t, right? In this case, we're dealing with a negative 1,609 meters, and a positive 4.695 seconds. All right, and so we see a couple major differences. One is positive, one is negative, and the other one is that the times are different. Now notice just very briefly here, this time over here, 4.695 seconds, is less than this time over here in run 1. So what's that telling us? Well, that means that it must be going faster. For it to cover that same distance in a shorter period of time, we should have a greater velocity, and we'll see that when we get our final answers here. All right, so the velocity for the first part of the run, all we have to do is divide here. We get our 1609 divided by 4.740, and we get an answer of positive 339.45 meters per second. Meters over seconds is meters per second. All right, and over here on the right, negative 1609 divided by 4.695 seconds gives us an answer of negative 342.71 meters per second. And there we go. So those are the two velocities of the car in run 1 and in run 2. All right. In our third example here, we have a straight track that's 1,600 meters in length. The runner begins at the starting line, runs due east for the full length of the track, turns around and runs halfway back. The time for this run is 5 minutes. What is the average velocity and what is the average speed? All right. Now this is asking us again two different questions. One is for velocity, one is for speed. Now what's the difference between velocity and speed other than direction? Is that velocity uses displacement while speed uses distance. So for us to use these two equations, we need to establish both the distance and the displacement. All right, and so I'm going to just start with the picture. Again, I have a starting point. All right. Ooh, I don't want that thing. All right, so I have a starting point. This is my starting initial position. I'm going to call it 0 meters. And the runner is going to run due east for 1,600 meters, right? So over here, 1,600 meters. And then turns back and runs to this point. He runs back and a halfway, which is 800 meters. All right, back in the other direction. And this is going to be his final position. Well, if the total distance is 1,600 meters and he runs backward 800, then he must be located at 800 meters from the initial position. So the distance or the displacement from here to here, this must be 800 as well. So that makes his final position 800 meters in the positive direction. Well, how are these two things different? All right, so how do we use all this information? First, if I'm talking about displacement, then I'm talking about positions. All right, and so if I'm listing my givens for my velocity, all right, so for my velocity calculations, all right, we want to know what the velocity is. That's my unknown. We also do know our initial position is 0 meters, and our final position is positive 800 meters. And then over here, we can also say that we know the time that's up here in the problem takes him 5 minutes. All right, now 5 minutes is 300 seconds. And so when I go to do my calculation here for velocity, I'm going to use my velocity equation. All right, is going to be x final minus x initial over delta t. Now remember, delta x, our displacement, is the same thing as the final position minus the initial position, and I can use that right in this equation. All right, and so my final position here is 800 meters. All right, my initial position was 0 meters. That was where I started from over here. All right, and my time here was 300 seconds. Which gives me a velocity of, now you should type this into your calculator, right? Positive 2.67 meters per second. Positive because it's to the right. All right. So here I'm using my displacement, not my distance. And that's going to make a difference because in the second part, when we're calculating speed, we're using distance, not displacement. Okay? And so in this case, when I'm calculating speed, so speed is my unknown, the distance that this guy travels, all right, is going to be 1,600 meters plus the 800 on the way back. So that's going to be a total distance of 2,400 meters. The time is still 300 seconds here, all right? But notice that distance is different from the displacement. And when we substitute that into our speed equation here, how did I pick it? Well, look, S, D, and T, there's only one equation that has all those things in it. My distance, 2,400 meters, 300 seconds down here. Speed is going to be 8 meters per second. All right. So compare that to the velocity, which was much lower. Well, I mean, why is it lower? It's because he turned around and came back. We lose all of that extra distance that he ran because displacement only accounts for the starting and ending positions. It doesn't account for the path that the person actually took. Speed takes account for that. So we do get two different answers here. All right. So one last example. All right, for velocity. And in this case, we have a curious cat named Curious again. All right, begins his journey. And in this case, we're going to see a few different looking kind of things. All right, but I want to draw a nice picture. All right, he begins his journey 8 meters east of a small river cottage. All right, well, this is a dead giveaway that it is a position because we're referencing the cottage. All right, it's not saying he's walking 8 meters. It says that he's positioned 8 meters from a cottage. So there's my cottage. All right, and I have my little cat over here. Meow. Right, and he's starting at this position. So that's my initial position of 8 meters east, which is a positive 8 meters. All right. And he is walking his way to the west, just like so, until he reaches this river over here. Rivers are blue. And this is his final position, where the river is located. All right. Now, do I know this value? No, it's not given to me. In fact, that is what I'm solving for. Where is the river located? All right. So if he's walking to the west with a velocity of 16 meters per second, all right, how do I know it's a velocity? Because of the meters per second. And westerly direction means negative 16, all right, and that's one of my other givens here. What else do I know? I know the time that it takes him to do this is going to be 3 seconds. So what equation am I going to use? Same equation that I used before. All right, velocity is final position minus initial position over the time. All right. Oops. Oop, oop. I don't know what's going on here. So it is the time. All right, so we are going to substitute all the values that we know. We know that this is a, try this again. We know that this is a negative 16 meters per second. All right. The final position is what we're looking for. That's where the river is located. Our initial position is positive 8 meters. All right, and our time here is 3 seconds. So what do I have to do? I'm going to multiply by 3 first. All right, that's going to cancel the 3's out here on the right side so that I can start getting rid of this 8. I can't do this out of order. I have to do it in this order to get to the final position there. All right. So once I've multiplied that, I get a negative 48 meters is equal to x final minus 8 meters. All right, that's what the right side simplifies to. And so now I'm going to add 8 to both sides, and I'm going to get a final position of negative 40 meters, which in this case means that the river is located 40 meters west of the cottage. All right. And so there we saw 4 examples of velocity and speed. All right. Paying close attention to units, that's what helps us identify the correct equations. Good pictures are always going to help us out too, so don't forget to draw all of those. All right, there you go. We'll have another video here in just a minute for acceleration.